Polar versus non-polar. Equal sharing versus unequal sharing. Okay? Polar, remember, is the unequal sharing of electrons. Non-polar, there's no pull in electrons, that is equal sharing. So a molecule's properties will depend on its polarity. Some properties of molecules will depend on the polarity of the molecule. Polar molecules have a stronger attraction. Well, that's because on polar molecules, when it's unequal sharing, you have one side of the molecule that is negative, the other side that is positive. So that positive-negative attraction between them is what makes them stronger. So more energy is needed to separate polar molecules and nonpolar. So polar molecules are stronger, nonpolar molecules are weaker. Boiling points are higher for polar molecules. So the book gives you these list of procedures to determine whether it's polar or not. And to be honest, being online, it's going to be a little difficult to follow those. So I'm going to try to give you just a general consensus of determine polarity. If the molecule is symmetrical all the way around, okay, all the attachments are the same, top, bottom, left, and right. If it's symmetrical all the way around, it is going to be nonpolar. If the molecule is not symmetrical, it will be polar. So I'm going to do a couple examples. Okay, the first one is H2O. And if you draw H2O, you're going to start with oxygen, and it's 6 valence electrons. And it's bent shape. Now, at first look, you say, well, this might be symmetrical. It is symmetrical left to right, but if you look at the attachments are not the same. We have a hydrogen, and then 2 lone pairs. If there was 4 hydrogens attached, it would be symmetrical. But since there is these lone pair of electrons here and hydrogens here, it is not symmetrical. So therefore, this is a polar molecule. Okay? What happens here is hydrogen and oxygen have each their own unique electronegativity values, their ability to gain an electron. Well, oxygen is closer to fluorine, so therefore oxygen is what we call the electron hog. So what happens is on this side of the molecule, on the oxygen side, we have a negative charge because the electrons that are being shared here are being hogged by the oxygen, okay? And then on the hydrogens, since they are not hogging the electrons, there is partial positive charges there. So water is a polar molecule, okay? It has positive and negative charges. I should say partial negative, partial positive. Okay, this is a polar molecule. Water is very strong, has a very high melting point, very high boiling point, has surface tension, a lot of things determined by the polarity of water. Let's look at carbon dioxide. Carbon dioxide, when you draw the Lewis structure, is linear. And if you look at both sides of carbon, it's symmetric. There's an oxygen on both sides. Since this is symmetrical, it is going to be nonpolar. It is the linear shape, and it is nonpolar. So when you are looking at your shape sheet, there is a few shapes that will always be polar. And the two that will always be polar, no matter what, are the trigonal pyramidal and the bent. The reason why these two are always going to be polar, or unequal sharing, is because in the bent, you're going to have 2 atoms down here connected, and then you have 2 lone pairs. There will never be the same all the way around. There will always be something different on the top and bottom. Trigonal pyramidal is the same thing. You have these lone pair of electrons here, and then 3 atoms down there. These will never all 4 be the same. So therefore, these 2 shapes will always be polar every time. There's no way they can be nonpolar because they will never be the same attachments all the way around. The other ones, the top three, you just have to look. If all 4 attachments on tetrahedral are the same, it's going to be nonpolar. If there's one oddball, it becomes polar. Same with trigonoplanar. If all 3 of these attachments are the same, it's going to be nonpolar. If one of these attachments is the oddball or different, it's going to be polar. And the same thing with linear. We just did one that was nonpolar. Okay, if one of these is, let's say, bromine and the other one's chlorine on the other side, it's going to be polar molecule because the attachments are not the same. So just looking at some of the ones on your worksheet from yesterday that we went over. I'm not going to go over all these, but just a few of these. You are doing the last column that says polarity over here. On the first one, is iodine and chlorine the same? No, they're not. So this one is going to be polar because they're not the same. If it was iodine and iodine or Cl and Cl, it would be nonpolar. But since these are not the same, it's not symmetric, therefore it is polar. Number 2, we have silicone and all 4 attachments are the same. Fluorine, 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 and fluorine. Since it is symmetrical, top, bottom, left, right, all the attachments are the same, this one is going to be nonpolar. Number 3, look at nitrogen. You have 3 hydrogens and a lone pair of electrons. Are all 4 attachments the same? No. Therefore, this one is going to be polar. The shape of trigonal pyramidal is always going to be polar because you're always going to have a lone pair and then 3 atoms down below. Bent, that shape is also going to be polar. Why? Because you have 2 lone pairs and 2 hydrogens. All 4 attachments would have to be the same to be nonpolar. So this is polar. Number 5, chlorine, 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 chlorine. This is symmetrical. All the attachments are the same. Therefore, this is nonpolar. Okay? I'll do one more from the worksheet just so we're all clear. This one is boron and it has 3 hydrogen attachments. Since all the hydrogen attachments are the same, it's going to be nonpolar. If one of these hydrogens was replaced with something else, it would be polar. But since all the attachments are the same, it's going to be nonpolar. So that is the shortcut to determine polarity. Okay, I didn't use the book in their method, but if you just look at the symmetrical, look at what's being attached. If everything that's being attached and bonded to is all the same to the central atom, then you can say, hey, it's going to be nonpolar. If there's an oddball or if there's a lone pair of electrons, it's going to be a polar molecule. So you are finishing up that last column and turning things in. Everything is due by 3 p.m. today. I did want to show you the answer key to the sig figs from yesterday. For those of you that stuck around and actually watched this video, you can go ahead and take a look at these and make sure that you have them correct. The students that didn't watch the video will not get all the answers like you guys will. So enjoy and have a good weekend.